Hello! In this video, I'm going to be talking about continuity. That is, what it means for a function to be continuous, and why that matters, and how that relates to limits. So, if you've watched my other videos about limits, or you've just studied limits elsewhere, you know that the key idea behind limits is that the limit, as x approaches some particular number, does not depend on what happens when x equals that number, but only on what happens when x is close to that number. So, in the three graphs shown here, the only difference between those three graphs is what happens right at x equal to 2. They all have the same limit as x approaches 2 because the functions all do the same things when x is close to but not equal to 2. In this first graph, f of 2 is 3, and that matches what happens when x is close to 2. So that would be a continuous function or a continuous graph. In the second graph, there's a missing point there, showing that f of 2 does not exist. So right when x equals 2, the function's undefined, but the limit still exists. And in the third graph, f of 2 is -1. There's a point sort of completely out of place that doesn't match what's happening when x is close to 2. So what happens at 2 and what happens when x is close to 2 are completely different things. The limit is 3, but the value of the function right there at 2 is -1. And so that's also an example of a function that is discontinuous or not continuous at x equals 2. So remember, the limit as x approaches c of f of x doesn't have to have anything to do with f of c, with what happens to the function when x equals c. It doesn't have to have anything to do with it, but it usually does. That is, with a nice, predictable, well-behaved function, the limit will be the same as just f of c. And continuity is kind of a way of giving a precise mathematical meaning to what we mean when we say a nice, predictable, well-behaved function. So, in the case where that happens, where the limit as x approaches a number is the same as what happens when x equals that number, we say that the function is continuous at that point. So continuous graphically means that if you're looking at the graph of the function, it doesn't have any holes or gaps or jumps. It's all connected, all in one piece. Here are some examples of functions that are discontinuous, that is, not continuous at x equals 2. A couple of them we've already seen. This one here that has a missing point because it's undefined there. This one here that has sort of an out-of-place point that's defined to be something different from what the limit is. And then this one here where you get this sudden jump from one level up to another. You have one thing going on when x is a little bit less than 2, and something completely different happening when x is a little bit greater than 2. So there's a discontinuity right there. And then here, where there is no point on the graph where x equals 2, and even if there were, it wouldn't match up with what's happening on either side of that, because as x gets close to 2, the graph just shoots way up to infinity. And so we have a discontinuity, in this case an infinite discontinuity, there at x equals 2. So these first two are what we call removable discontinuities. The function is discontinuous there, but we could remove the discontinuity by plugging the hole, by changing what happens just right when x equals 2 to match what's going on when x is close to 2. The other two are non-removable discontinuities. There we can't remove the discontinuity and fix the function so that it is continuous just by changing or redefining what happens right at that one point. So now for the official definition. A function f of x is continuous at x equals c if the limit as x approaches c of f of x equals f of c. I pretty much already told you that this is what continuous means, but this definition here is really three conditions in one. There's three things that have to be true for a function to be continuous. First of all, it has to be defined. F of c has to exist. If it's undefined, the function can't be continuous. Condition number two, the limit has to exist. The limit as x approaches c has to exist. If the limit doesn't exist, the function is discontinuous. And these two things have to be the same as one another. They can't be two different numbers. So if any one or more of these conditions is not true, the function is not continuous. It's discontinuous at x equals c. And we can get a little bit more specific about why a function is discontinuous or what kind of discontinuity it is. A removable discontinuity is one where the limit does exist, but right at that point, the value of the function is either undefined or it has a different value from what the limit is. It could be undefined at 2, or it could be defined to be something different at 2 from what's going on when x is close to 2. Those are removable discontinuities because we could remove the discontinuity and make it continuous just by defining or redefining the value of f of c to be the same as what the limit is. So in both of these graphs, if I just said, okay, I'm going to make f of 2 be 3. So instead of being undefined or being some other number, it's now 3. So it matches all the other nearby points. There I've removed the discontinuity. I've made it continuous. A jump discontinuity is where the limit as x approaches c from the left and the limit as x approaches c from the right are two different numbers. Both of those one-sided limits exist, but they're not the same as one another. So it's like you have two pieces that do not meet up. You have this sudden jump from one level to another without going through the points in between. And then an infinite discontinuity is one where you have an infinite limit. The limit as x approaches c, either from the left or from the right or both, is infinite. It either equals infinity or it equals negative infinity, or possibly one of those from one side and the other from the other side. Now here are some other ways to think about what it means for a function to be continuous. It means the function is well behaved and predictable. It does what you would expect it to do. A small change in x corresponds to a small change in f of x. And if it's continuous, then suppose I cover up part of the graph with a very thin vertical strip of tape. When I uncover it, when I peel off that tape, there will be a point there, and it will be where you would have expected it to be. So let me show you what I mean by that. Here are some graphs with a thin strip of tape covering up what happens when x equals 2. Now, if you just look at the rest of the graph that isn't covered up, you would guess that there should be a point there at 2, 3. The point on the graph with an x-coordinate of 2 ought to have a y-coordinate of 3 if it's going to sort of match the part of the graph that you can see. With this first graph, that is in fact what's happening. So that one is continuous. With the second graph, I pull off the tape and surprise, there's a missing point there. Ha, you weren't expecting that. There's no way to tell it's missing when that part of the graph is covered up. So since it wasn't what you expect, that's a discontinuity. And what about this? Again, you think there's going to be a point right there, but fooled you, it's actually way down here. It's not where you would have expected it to be. So that's another discontinuity. And if you look at this graph, where do you think there ought to be a point at x equals 2? Well, there isn't really a place that would fit with all the other nearby points. We can't put it down here because that wouldn't match with these points. We can't put it up here because that wouldn't match with these. Anywhere else wouldn't match with anything. So there's no one point I could put that would fit in and be close to all the other points that you can see here. So we have this jump discontinuity. And then here, there's nowhere I can put a point right at x equals 2 that will seamlessly match with all the other nearby points. Okay, so far we've been talking about what it means for a function to be continuous at some specific point, or some specific number, some specific value of x, the independent variable. But you can also talk about what it means to be continuous on an interval for a whole stretch of values of x. So we can talk about a function being continuous on an open interval, and that would just mean that it is continuous at every point in that open interval. Remember, an open interval, that's one that's written with round parentheses, is one that does not include its endpoints. So for example, the open interval from 1 to 2, so round parenthesis 1, comma 2, close parentheses, would refer to all of the real numbers that are strictly between 1 and 2. Everything that's greater than 1 and less than 2, but not including 1 and 2 themselves. A function is continuous everywhere if it's continuous on the interval from negative infinity to positive infinity. That is, continuous at every real number. It doesn't have any points where it's undefined or doesn't have a limit or is discontinuous in any way. And then it gets a little bit trickier to say what you mean by being continuous on a closed interval. A closed interval, written with square brackets, does include its endpoints. So the closed interval from 1 to 2 would include the numbers 1 and 2 as well as everything in between. And what's tricky about that is we don't want continuity on a closed interval to depend on what happens outside that interval. So we can't just say it has to be continuous at every point in that closed interval, because to be continuous at, say, the endpoint a would mean that the limit as x approaches a would have to exist, and that would depend on all of the x's that are close to a. But some of those numbers that are close to a are a little bit less than a, which would put them outside the interval. So the way we define continuity on a closed interval is to say, first of all, it has to be continuous at every point in the interior of the interval, every point strictly between a and b. And then, if you look at the limit as x approaches a from the right, from inside the interval, that has to equal f of a. And if you look at the limit as x approaches b from the left, which is also from inside the interval, that limit has to equal f of b. Now, if you looked at my video on finding limits analytically, or if you'd studied that elsewhere, you saw a whole bunch of theorems or facts or limit laws about how limits work that tell you things like the limit of the sum of two functions is the sum of their limits, provided both limits exist. And the limit of a quotient is the quotient of the limits, provided both limits exist and you don't have a zero in the denominator. Things like that. And then all of these facts about limits kind of give rise to a fact about continuity. For example, since the limit of the sum of two functions is the sum of the limits, that means if you have two functions that are separately continuous at the same point, their sum, the function that you get when you add them together, must also be continuous at that point. If you have two functions that are both continuous at a point, and you take their quotient, f over g, that is also continuous as long as the denominator is not 0. If the denominator is 0, then the whole thing, f over g, would be undefined because you can't divide by 0, and so you would have a discontinuity there. But as long as that doesn't happen, if the function on top is continuous and the function on the bottom is continuous, then f over g is also continuous. And there are lots of more facts like this. I'm not going to list them all, but you could probably find a complete list in a calculus textbook. And they're all pretty much straightforward and what you would expect to be true. And as a result of all of that, we can say that polynomial functions are continuous everywhere. If you have a function that is just a polynomial, there's no places where it's undefined. There's no places where it does anything unexpected, takes a sudden jump, or shoots way up to infinity. The graph of a polynomial function is nice and connected and all in one piece. So yeah, polynomial functions are continuous everywhere. And rational functions, those that are a polynomial over another polynomial, a ratio of two polynomials, those are continuous everywhere except where the denominator is equal to 0. If the denominator is 0, then of course the function would be undefined at that point, and you could have a removable discontinuity at a point like that, because the limit could still exist, or you could have an infinite discontinuity. And that would happen if the denominator approaches 0, but the numerator does not. And then some of your favorite transcendental functions, like the trigonometric functions, exponential functions like e to the x, logarithmic functions like ln of x, those are all continuous everywhere they are defined. So that means sine and cosine and e to the x are continuous everywhere. Tangent and secant are continuous everywhere except for the places they are undefined. They have infinite discontinuities at the points where, well, it would be the same points where cosine of x is equal to 0. So that would be at positive or negative pi over 2, 3 pi over 2, 5 pi over 2, etc. Cotangent and cosecant are continuous everywhere except for the points where they are undefined, which would be the integer multiples of pi. So 0 and positive or negative pi, 2 pi, 3 pi, and so on. And then the function ln of x, the natural logarithm function, is continuous on its domain, which is the positive real numbers, the open interval from 0 to infinity. So let's look at some examples. We'll look at some specific functions and decide where they are continuous. Or we could start by deciding where they are discontinuous, and then they'd be continuous everywhere else. So what about f of x equals x cubed minus 7x squared plus 11x plus 6? Where is that continuous? Well, it's a polynomial, so it's continuous everywhere. That is, on the interval from negative infinity to infinity. Here's what the graph looks like, or at least as much of the graph as fits in this square here. And you can see it does look continuous. It does look like it's all in one piece with no holes or gaps or jumps or anything like that. And on all of these examples, I'm going to be showing you the graph, but only after we've decided where it's continuous, because I want to get some practice in deciding where a function is or is not continuous by analyzing how the function is defined or put together before we look at the graph. How about this one? F of x equals x minus 1 over x minus 2. Where is that continuous? Or where is it discontinuous? Well, it is a rational function, so it's continuous everywhere except where the denominator would equal 0. And for this function, with this denominator, that denominator would be 0 when x is 2. So if x is 2, if you plug in 2 for x, you get a 0 in the denominator, division by 0 error, it's undefined, but it's continuous everywhere else, everywhere except 0. So where it is continuous would be the interval from negative infinity to 2, not including 2, and the interval from 2 to infinity, again, not including 2. That is, it's continuous everywhere except 2. And that discontinuity at 2 is non-removable. It's an infinite discontinuity. I know that because the numerator is not 0 there. We get a numerator that's approaching 1 over a denominator that's approaching 0. So we get an infinite limit, something that's going to, well, it would be going to infinity on one side and negative infinity on the other side. See? There's the graph with the infinite discontinuity at x equals 2. Okay, what about this one? F of x equals x squared minus 17x plus 70 over x squared minus 49. This is another rational function, and it might be easier to see what's going on if we factor the numerator and the denominator. So the numerator can be factored into x minus 10 times x minus 7, and the denominator can be factored into x plus 7 times x minus 7. And again, it would be continuous everywhere except where the denominator is equal to 0. So in this case, that would be everywhere except when x is negative 7 or positive 7. So the intervals where this is continuous would be everywhere in between and on either side of those two bad points. So the open interval from negative infinity to negative 7, the open interval from negative 7 to positive 7, and the open interval from positive 7 to infinity. Now, if you want to be a little bit more specific about what happens at those two bad points, at x equals 7, we have a removable discontinuity. Notice there's a factor of x minus 7 in the numerator and in the denominator. We could cancel out that common factor and sort of reduce it to just x minus 10 over x plus 7, and then that would be continuous at x equals 7. We would have removed the discontinuity. So this is an example where the function is undefined at 7, but the limit as x approaches 7 would still exist, and so there's just one missing point with all the other nearby points in place, and we could remove the discontinuity just by sort of fixing what happens there at that one point. But we have a non-removable or infinite discontinuity at negative 7. I can tell that because as x approaches negative 7, the denominator is approaching 0, but the numerator is not. So here's the graph. It's got just one missing point at x equals 7. So that's our removable discontinuity. And then we've got our infinite discontinuity at negative 7. What about this one? F of x equals the absolute value of x over x itself. If you've seen my other videos on limits, you've seen this function before. And you know that it gives you a value of positive 1 anytime the number you put in for x is a positive number, one that's greater than 0. And it gives you a value of negative 1 if the number you put in for x is a negative number, less than 0. So you have completely different things happening on either side of 0. And so as long as we stay on one side or the other of 0, the function is just always 1, or it's just always -1. It's nice and continuous. It is continuous on the interval from -infinity to 0, and also on the interval from 0 to infinity. But right there at 0 is where we have this sudden jump from -1 up to +1. So there's a non-removable or jump discontinuity there at x equals 0. And you can see that on the graph. Here it's continuous, then we have this big jump here, this gap, and then it's continuous the rest of the way. What about this one? Now this is a piecewise defined function. It's defined in 3 separate pieces. What it does to x depends on what kind of number x is. So f of x gives you x squared if x is less than -1. It gives you x plus 2 if the number you put in for x is greater than or equal to -1 but less than 1. And it gives you -x squared, remember that's negative x times x, if x is greater than or equal to 1. So as long as x stays on one of those 3 intervals and doesn't cross over one of those dividing points, then the function behaves like one of these continuous polynomial functions. So this function is at least continuous on the interval from -infinity to -1, and on the open interval between -1 and 1, and on the open interval between 1 and infinity. What we still have to figure out is whether it's continuous or discontinuous right at -1 and right at +1. That is, do the pieces match up or not? If they match up, it's continuous there, and if they don't match up, if you have different things from the left and from the right, we've got a jump discontinuity. So first of all, let's see what happens right around when x is -1. Does what happens when x is a little bit less than -1 agree with what happens when x is a little bit bigger than -1? As x approaches -1 from the left, f of x would be behaving like x squared, and so it would be approaching -1 squared, which is +1. So that's the limit from the left. As x approaches -1 from the right, so now we're considering x's that are greater than -1 by just a little bit. Now f of x is giving you x plus 2. And as x approaches -1, that would be approaching -1 plus 2, which would be 1. So we have the same limit from the left and from the right. And so that is the limit as x approaches -1. That limit is 1. And then f of -1 would be -1 plus 2, so it would be 1. And that matches what the limit is. So everything agrees it is continuous at -1. What about at x equals +1? As x approaches +1 from the left, so we're looking at x's that are a little bit less than +1, and the function is giving us x plus 2 as a value. So the closer x gets to 1, the closer f of x gets to 1 plus 2, or 3. So that's the limit as x approaches 1, +1, from the left. If x is approaching 1 from the right, now we're looking at what happens when x is a little bit greater than 1. And now f of x is giving us -x squared. And as x approaches 1, that's approaching -1 squared, which is -1. So the limit from the left is 3. The limit from the right is -1. Those do not match up. So the limit just as x approaches 1, and sorry, there should not be a minus sign there. As x approaches 1, the limit does not exist. And since the limit doesn't exist, the function is discontinuous. And even more, since the limit doesn't exist, it's a non-removable discontinuity. We have a jump discontinuity. So if you want to look at the graph, well, to sum up, our function is continuous everywhere except 1. That is, from negative infinity to 1, and then from 1 to infinity, but not including 1 itself. So here's the part where x is less than negative 1. Here's the part where x is between negative 1 and 1. Here's the part where x is greater than or equal to 1. It's continuous there at negative 1, but we have this big jump discontinuity at positive 1. Okay, what about if f of x equals the square root of x plus 9? Well, x plus 9 itself would be continuous everywhere. And then if you take the square root of that, that's continuous as long as we're not trying to take the square root of a negative number, because that would be undefined since we're just working with real numbers. So the thing that we are taking the square root of, the radicand, must be greater than or equal to 0, which means that x itself has to be greater than or equal to negative 9. That would be where this function is defined, and then it would be continuous. So it's continuous everywhere on its domain, which is the closed interval from negative 9 to infinity. What about f of x equals the sine of 1 over x? Where is this continuous? Where is it discontinuous? Well, it's undefined at 0. X can't be 0 because then 1 over x would be undefined. And so it must be discontinuous there. If it's undefined at a point, then right away you know it's discontinuous at that point. It's harder to be continuous than it is to be defined. So if you're undefined, you're automatically discontinuous. If you're defined at a point, you still might or might not be continuous. Everywhere else, besides 0, the function 1 over x would be continuous, and then the sine function is continuous everywhere. So that composite function, where we're taking the sine of 1 over x, would be continuous everywhere those two individual functions are continuous. That is, everywhere except 0. So the open interval from negative infinity to 0, and the open interval from 0 to infinity. The limit as x approaches 0 of the sine of 1 over x does not exist. I've discussed that a little more in one of my other videos. So the discontinuity at 0 is non-removable. The reason continuity is important, or at least one reason continuity is important, is because there are a bunch of theorems that take as part of their setup, their requirements, that the function that you're talking about has to be continuous. They start out as something like, let f be a continuous function, or suppose f is continuous on some interval. So one example of a theorem like that is the famous intermediate value theorem. So the intermediate value theorem says that if a function f of x is continuous on a closed interval from a to b, then f takes on every value between f of a and f of b. It takes on all of those intermediate values that are between what it takes on at a and what it takes on at b. Another way to say that is, if k is any number between f of a and f of b, there must be at least one number c, one x value c, somewhere between a and b, such that f of c equals k. So really, this just means you can't get from one point to another without going through all of the points in between. You can't take on one value and then later take on another value without taking on all the intermediate values if the function is continuous. So let's look at an example to try to get a feel for what this is telling us. Take the function f of x equals x squared minus x minus 5. This is a polynomial function, so we know it's continuous everywhere. I can pick any interval I want, and it's going to be continuous on that interval. So the particular interval I want to look at is the closed interval from 2 to 3. It's continuous everywhere, so it's continuous on that particular interval. So here, the interval from a to b in this particular example would be the interval from 2 to 3. Now, f of 2, when you plug 2 in for x, you get negative 3. You can see that on the graph. There's a point on the graph with an x coordinate of 2, and it's got a y coordinate of negative 3. And what happens when you plug in the right endpoint, 3? Well, f of 3 is 1. So there's a point on the graph where x is 3 and y is 1. And so the intermediate value theorem says that you can't get from down here at negative 3 to up here at 1 without going through all the values that are between negative 3 and 1. So since 0 is one of those values between negative 3 and 1, there must be at least one x somewhere between 2 and 3 where f of x is equal to 0. It doesn't have to be 0, just 0 is one example of a number between negative 3 and 1, but I could have picked any other value between negative 3 and 1. So there's at least one x between 2 and 3 where f of x is negative 2. And there's at least one x between 2 and 3 where f of x is 0.12345, and so on. But often zeros are numbers that we're especially interested in. Now, the intermediate value theorem just says that there is at least one x like that. It doesn't tell you what that x is, but we could figure out exactly where that is by solving the equation x squared minus x minus 5 equals 0 with the quadratic formula or something like that. Or we could get an approximate value, narrow it down even more than just somewhere between 2 and 3, by doing some further calculations. Suppose instead of just plugging in the numbers 2 and 3, we plug in some other numbers in between. Here I've plugged in 2 and 2.1 and 2.2 and 2.3 and so on, all the way up to 3. And if you look at the values here, where it goes from negative to positive is somewhere between 2.7 and 2.8. So f of 2.7 is less than 0, f of 2.8 is greater than 0, so somewhere in between 2.7 and 2.8 is where we hit 0 exactly. And if I want to narrow it down further, I can calculate some values that are between 2.7 and 2.8 and look for where the values change from negative to positive. And that happens somewhere between 2.79 and 2.80. So f of 2.79 is a negative number, less than 0. F of 2.8 is a positive number, greater than 0. So somewhere in between 2.79 and 2.8 is where we hit 0 exactly. If I want to narrow it down further, I can see, f of 2.791 has a negative value, but f of 2.792 has a positive value. So the exact x where f of x hits 0 exactly must be somewhere in between 2.791 and 2.792. That is, it must be 2.791 something. And by doing more calculations, we could get more decimal places. And so this sort of brute force, lots of calculations approach is one way that you could at least approximate the 0 of a function. And it may be how your graphing calculator does it. If you have a graphing calculator that could give you approximate zeros of a function. Now, it is important that the function be continuous. Look at this example. Take the function g of x equal to 4 over 2x minus 5. If I plug in 2, g of 2 turns out to be negative 4. 2 times 2 is 4, 4 minus 5 is negative 1, and 4 over negative 1 is negative 4. And g of 3 is positive 4. 2 times 3 is 6, 6 minus 5 is 1, 4 over 1 is 4. So g of 2 is negative 4, g of 3 is positive 4, 0 is somewhere between negative 4 and 4. Does that mean that there must be at least one x between 2 and 3 where g of x is equal to 0? Well, no, not necessarily. The intermediate value theorem does not apply here because this is not a continuous function. It's not continuous on the interval from 2 to 3. It's got that discontinuity at 2.5, 2.5, which is between 2 and 3. Okay, one last little remark. The functions that you're used to working with are either continuous everywhere they're defined, or they have maybe one or two or just a few discontinuities. But functions can get weirder than that. Functions can have more than just one or two discontinuities. In fact, I could give you an example of a function that's defined everywhere, so you can plug in any number you want and it will give you a value, but it's continuous nowhere. It's discontinuous at every point. And that function is what's called the Dirichlet function. It's the function where f of x is 0 if x is a rational number, and 1 if x is an irrational number. Remember, the rational numbers are the ones that you can write as a ratio or as a fraction, and the irrational numbers are the ones that you can't. And if you try to write them in decimal form, the decimal digits keep on going forever without repeating. Now, no matter what real number you pick, there are always going to be other numbers that are really, really close to that that are rational. And there are also going to be numbers really, really close to that that are irrational. And so there's no one value that all of the numbers close to x are all close to. Some of them are close to 0, others are close to 1, and so the limit does not exist as x approaches any particular number. And since the limit doesn't exist, the function can't be continuous. And then here's an example of a function that's defined everywhere, but continuous only at the point x equals 0. And that would be the function that's equal to 0 if the number you put in for x is a rational number, and it's equal to x if the number you put in is irrational. Now, whenever x is close to 0, g of x is either equal to 0 or it's equal to x, which I just said was close to 0. So it's always close to 0 when x is close to 0. And that matches what happens when x equals 0. And so it is continuous there. But it's not continuous anywhere else, because for any other number other than 0, you get values close to that number that are close to that number. And you get other values close to that number that are 0, which is enough different from that number that you don't get arbitrarily close. You can't come as close as you want. So that was a look at continuity, what it means for a function to be continuous and how that relates to limits.